Okay, welcome back to lecture 4.4, where we're going to do 4.4. We're going to do isobaric and isochoric compression. So these are a little bit easier than the isothermal compression, so I thought we would do them together. Okay, so isobaric, remember, of course, means constant pressure. Right, that's the bar in baric. And so the question is, how do we set up to make an isobaric system? So let's draw our piston system again. So let's draw our piston. Again, it's woo. Let's try that again. Wow. So it's not great. Okay. So we have an ideal gas. Right? So we have an ideal gas again. We're going to have a bath. But this time the bath, we're not going to fix the temperature. We're going to allow it to change. Okay? So we imagine a situation where, imagine we fix the, we're going to fix the pressure. And how do we imagine making a constant pressure? Okay, so you can do this by realizing that our piston has an area A. And so what we could do is we could actually add a weight to it, right? Put a mass M on our piston. Okay, so what that would result in is a force pushing down on our piston, right? But because we have a constant area, a constant force is a constant pressure, right? So now what we're going to do is, now you can vary the temperature of the bath, and since we have diathermal walls, that means that when we change the temperature of the bath, we're going to change the temperature of the system, right? So last time we had fixed temperature, but now we're going to vary it. So the way you can think about doing this is like when you did the constant volume gas thermometer experiment in undergraduate labs, you had your little glass bulb sitting in a bath of water, but then you could apply heat with a Bunsen burner, or you could add some ice. You could vary the temperature of the bath. So that's what we're thinking about how to do that here. So this is a very similar scenario, except here is constant pressure. That one was constant volume. We'll do constant volume next. Okay, so what we realize is that we need to think about our equation of state. So if we fixed the pressure, right, and we vary the temperature, let's say we take the temperature and we cool it down, then the volume will go down, right? So if we cool it down, the volume will go down. And so if we look on a PV indicator diagram, we're going to do constant pressure. So let's start at V1, constant pressure. The volume's going to go down, and so we're going to go from state 1 to state 2 to V2, right? So at a constant fixed pressure. Okay, so what's the work done in that process? Well, the work when we go from 1 to 2 is minus the integral from state 1 to state 2 of P dV. Ha, but now in this special occasion, since the pressure is constant, we can take it out of the integral. Minus P integral from 1 to 2 of dV. And so that's just minus P V2 minus V1. Okay? Let's check our sign convention. If V2 is less than V1, we had compression, right? And if we have compression, then here we see this is negative, that's negative, two negatives. That would mean that the work was positive. Little check mark. That's exactly what we wanted. Okay? That just meant that work was done on our system. Great. If we had flipped it around, obviously, if V2 were greater than V1, we'd be doing expansion, right? To do that, we would have to actually increase the bath temperature, right? Heat would have to flow in, the temperature would have to rise, and our piston would go up, our pressure, our volume would go up at fixed pressure. Okay, so that was isochoric. Let's do, sorry, that was isobaric. Let's do isochoric. All right, so isochoric means constant volume. All right, and so this is exactly the scenario of the constant volume gas thermometer, right? So what we can imagine, our piston now has a fixed lid, right? It can't change. We submerge that in our bath, right? This is an ideal gas again, right? And now we can vary the temperature, right? And see what happens. Well, let's look on our PV diagram. So let's draw it up. So our PV diagram, we're going to have some volume, right? We're going to start at 1 pressure. Let's say I lower the temperature of the bath. The pressure is going to go down, right? Now, what's the work done in that scenario? Well, the work when it's done from 1 to 2 is minus the integral from 1 to 2 of P dV, but we can see that dV was 0. Right? So no work was done in that scenario. Okay, that seems kind of funny because we did do something, right? We changed the temperature and hence the pressure. But we did change the energy, right? But we did not change the work, right? Because the work is the mechanical energy. And for the mechanical energy to change, we really have to change the volume. Okay, so that was isobaric and isochoric processes. So now what we're going to do, so also in general, you could have much more complicated scenarios. You could have things that only follow these paths part of the time, or you could have them, something that follows these paths none of the time, right? So these are just some very small subset of possible paths, right? But they're very nice to consider. Okay, so this is lecture 4.4. We're going to go on to lecture 4.5, and I'm going to talk about the path taken as we go around these loops.